Hi guys, Mrs. Delisin here. Welcome to another lesson of AP Statistics. Today's lesson is chi-square test of homogeneity. So when do we use this one and how is it different from chi-square test for goodness of fit? Alright, so we have is a distribution of gummy bear color, the same for Haribo gummy bears. I hope I said that right, and Meyer gummy bears. Will collect data as a class and determine if we have convincing evidence of a difference. We are going to add your data to the board and fill in the table below with the class total. So again, since we are not together and it's kind of hard for us to have an experiment together, so we are going to, actually this is not an experiment because we're just technically counting, right? So let us do our observed value. So imagine we have 63 Haribo gummy bears and 104 Meyer gummy bears. And we counted how many gummy bears for each color. So we have red, green, yellow, orange, and white. Okay, the blue are the number that we counted, and then the red is just the total. Okay, so we have 51, the total for the row in red. And then we have 22, the total for green. So we have row total and we also have column total. And we also have the overall total, right? So we need to make sure that you understand because we will be using them later. So we have a column total, we have a row, and then we have an overall, which is 163. How many samples do we have and what population are they from? So I'm not asking about like how many gummy bears, but we're being asked of how many samples, right? So we have two samples in here. Okay, we have two samples. And what are they? That's one sample from Haribo gummy bears, Haribo population. And we also have one sample from Meyer population. Okay, there you go. How many variables are we examining? So when you say variable, like is it a categorical variable or is this a quantitative variable? But in this case, you have a categorical variable, which is one variable, and that is the color of gummy bears. Okay, moving on. As a class, write down hypothesis for a significance test. Okay, this is how we differentiate the hypothesis from goodness of fit. Because in the goodness of fit, we're trying to say that for our null hypothesis that the distribution is true, right? The claim distribution is true. Like say the M&Ms, right? We were trying to assume that the color distribution given is true by the company, right? And then our alternative hypothesis were, no, it's not true. That the given distribution is not true. But in here, we're trying to see if there is a difference between the color in each of these gummy bears, right? So how do we say that for our HO? We say that there is no difference, right? Does that make sense? In the color distribution. There is no difference in the color distribution for, I always run out of space, yeah. For Haribo and Haribo. How do you say that? It doesn't matter. Gummy bears. There you go. And then our alternative hypothesis, there is a difference in the color distribution. Okay, there you go. For, of course, the same thing. All right, number 5. Now we will use a chi-square test to test if there is a difference between the two populations. But in order for us to do that, we have to find our expected value by completing the table. Now, in the chi-square goodness of fit, getting the expected value was so easy because all we have to do is multiply the total number of sample by the proportion of each in each category, right? So if we say 13% are red, so I'm going to say 0.13 times the overall total. But in this case, we're not going to do that. It's a little bit hard, not harder, but it's a little bit complicated. But you don't have to worry about it because I will never be I'm asking you to do it by hand because you can do it in the calculator, and I will be teaching you that in class. So how do we do that? We are going to do expected count. I'm going to put the formula here. Expected count, the formula is row total times column total. That's why I asked you for the row total and column total earlier, over the table total or the overall. Okay, so we're gonna do that unfortunately for each of these missing numbers. So I'm gonna start with maybe one or two, and then hopefully you can replicate what I'm trying to do. Okay, let's start for the red. What I'm going to do again, what I'm trying to get here is the expected value because my observed value is 20, but my expected value is I don't know yet. So what do? We are going to multiply my row total, which is 51. Okay, follow along. 51. Multiply that with the column total, which is 63. So that is 51 times 63. And I will divide those by 167. So that is just for red. Okay, where do we put that? Put that there, red. So red would be the expected value for red would be 51 times 63 over 167. And hopefully you will get 19.2. So what's the missing number here? It's 19.2. Moving on, let's get for, that is red H because that's for the first column. Now let's get the red for Meyer. There you go. So that is again your table, your row total times your column total is 104 over your table total. And or what I mean by table total is this one, 167. Hopefully you'll get 31.8. Okay? Does this make sense, you guys? Hopefully. So I'm going to continue with one last thing. Maybe let's get for green. Green H. Okay, so that is 22 times 63 all over 167. And hopefully you'll get 8.3. And just like that, we are done with our expected values over here. So I'm going to fill in over here because we don't really have to spend so much time in getting all of those answers. I'm pretty sure you guys already know how to do that. Okay, there you go. And if you're still writing, you can pause the video and finish writing all the numbers. And again, there is a way to get these in the calculator all at once with no problems. Okay, use your work on the front page to complete a 4-step significance test. So we're going to use the 4 process now. Okay, I already know, we already did, I'm not going to repeat that anymore. So see above, because we already did that. Our HO would be there's no difference in the color distribution, right? And our alpha level, if it's not given, we assume it's 5%. So let's check the condition. We always, again, check if it's random all the time. So we randomly selected the gummy bears. All right. And then 63 is less than a tenth of, because you know how I have 63 gummy bears, and then I have, how much do I have? 104 for the other one. Of all gummy bears. Okay, not that bad. All right. And then this is the same thing that our large count needs to be, or all expected counts needs to be greater than 5. It's the same as for goodness of fit. So there's no change in there. So large count, all expected counts. It has to be all, yeah? All expected counts. Let me go back to see if all my expected counts are all greater than 5. Yes, they are. So all expected counts are all greater than 5. Because this is to justify, because the lowest is green, Harbo, with 8.3. The expected value for green is 8.3. So therefore, or all expected counts are greater than 5. Okay, specific formula, really the same. Our specific formula is the same as the one for earlier. So what is really different, right? I think the one that is different is the conditions are the same. The how you say your hypothesis is different, and then how you solve for expected value is also different. But then the rest of it is the same. So we are going to show our work as usual. But then our work, this is too much, yeah? Do you notice that? So you remember that the show work, you just do 20, do the first two, and then the last one. Squared over 19.2 plus 31 minus 38.8 squared over 31.8 plus dot plus the last one. What's the last one? 19 minus 19.9 squared over 19.9. There you go. So you are going to get an x squared value here. I'm going to write it down, assuming that we've solved it all together. But again, I'll teach you how to do that in the calculator, because you don't have enough time to subtract how many? 1, 2, 3, 4, 5, right? To 5, 6, 7, 8, 9, 10. Ooh, that's a lot. Okay, so we are going to do our x squared. Our answer would be 2.93. There you go. And then we'll take our picture here, and I'm gonna tell you, oh, miss, skewed right distribution. Skewed right, boom. And I'm going to shade, that's a really big one. I'm gonna shade 2.93. Okay? So I'm gonna do both. I'm gonna do it in the calculator, okay? But before I go to the calculator, I'm going to do the DF. I'm going to do it in red because the DF in here is going to be different. You know how I did DF for goodness of fit is category -1. But in here, we really can't do category -1 because you know how we have a two-way table? We have a distribution for 2 samples. So there is another formula for it. Sorry. The formula for DF is now row -1, or the number of rows -1 times the number of column -1. It's so weird, yeah? So let's do number of rows. Number of rows excluding the total, of course. 1, 2, 3, 4, 5. And then we have 2 column. So this is, let's put that in red. Number of rows would be 5 -1 times number of column 2 -1. So this is 4 times 1. So our DF is going to be 4. And again, miss, what if I forgot the formula for that? If you forget, Don't worry because, unless it's a multiple choice, yeah. But don't worry because your calculator will give you a DF. Okay, so what else do we need? Oh, I forgot. There you go. X squared DF, which is 4. And then my test statistic would be, I already know that, 2.93. So I'm going to get my p-value to x squared CDF, the same thing. 2.93, comma 1000, comma 4. Our p-value is a really big number, 0.57. So we're going to make conclusion the same as usual. Our conclusion is because, I think the conclusion is the only one constant in everything, yeah? Because the p-value 0.57 is greater than 0.05, way greater, we fail to reject a null and do not have convincing evidence that there is a difference in color distribution. There you go. For, this is too much writing, yeah? For and Meyer gummy bears. All right, there you go. All done. Explain how this test is different from a chi-square test for goodness of fit. So how are they different? And it's very important that you know, because it's, you know how everything is the same except the top portion. So if you use the wrong method, you are going to lose a lot of credit. So in this, we have two samples. We have two samples. Maybe I have to. We have two samples from two population. Does that make sense? Two samples, two population. But for the x squared g of f has one sample from one population. Remember that? From one sample from M&Ms only. Okay, so that's the difference. So we have a chi-square test for homogeneity. We have two samples, two population. For goodness of fit, only one sample from one population. But if you notice, they're both categorical variables, right? Color of M&Ms, color of gummy bears. All right, there you go. Let's do our checking important ideas section. It looks like we have a lot to put in here. Okay, let's start with our HO. Okay, HO, we always say there is no difference. There is no difference in whatever variable, categorical. When I say categorical variable, like color, gender, classes, we learned that one already. Distribution. Okay, for population 1 and 2. And then our HA is there is a difference. Can I just say same thing? There is a difference. All right, what else? Expected count. There is too much to remember in this one. Expected count would be row total times column total over table total. There you go. And then for the condition, same thing. We check if it's random. You check 10% condition. And then you check for large count. And then our large count must be expected, must be greater than 5. Okay. What else? Oh, the difference between GOF and homogeneity. So we have color x squared for this one. What is this? 2 sample, 1 variable. Right? We had 2 sample of gummy bears, but we only have 1 variable in here, which is color. But then for x squared GOF, we have 1 sample, we have 1 variable. Looks so the same, yeah? All right, there you go. Let's try to practice. A social scientist selects a random sample of 25 freshmen, 25 sophomores, 25 juniors, 25 seniors from various high schools across the state Kentucky. Each student was asked if they preferred in-person or remote learning. Here are the results. Remote, 3, 12, 15. So we need to put a total value so that, remember, so that it's easier for us to do our expected count. So how many is that? 100. 25. Oh, this is great. Our column total is all the same numbers. Very good. Okay, so we are going to do letter A. Our HO, which is too many things to write. So we want to know, what do we want to know? We wanted to know if there is a difference between the number of students who would like remote and in person. Yeah, if there's a difference between the distribution. So we'll say there is no difference. That's our null. We assume there's no changes, there's no difference in the distribution of, what do we call this? Learning preference, right? Of learning preference for all freshmen, sophomores, juniors, and seniors. And we have to put their state. There you go. And then HA, there is a difference in the distribution. Can I just say that same thing? Okay. Show the calculation for the expected count in the remote senior cell, then provide a complete table for expected counts. Okay, again, we're going to use calculators later on, but for now, let's try to solve them. So what am I going to do first? Let me make a table first so that I can just fill it in. Oh. Okay. How many? 1, 2, 4, yeah? There you go. And then I name it remote and in person. Maybe I would actually put the word remote. All right. And then let's put the formula. What's the formula again? Formula is row total times column total over table total. So let me get the remote for, I didn't label, freshman, sophomore, junior, and senior. Okay, let me get for seniors. Okay, let's get for remote seniors. Just for example, I'm doing this first because it's close to the total. So I'm going to do senior in remote classes. Prefers remote classes. So let's do remote and senior. So row total 44, right? Times column total, which is 25, over 100. And that is 11. Okay, so this is 11. But then again, since they are all 44 and they're all 25, that means these are all 11. Does that make sense? Okay, so then what about this one? In person. Same thing, yeah, you only solve once. In this case, you only solve once and you get the whole entire row. But then on the previous question, we cannot because every column was a different number, right? Like, we have a different number of gummy bears. So it was a little bit harder. So in here, let's do 56. It's like if I want to get senior who prefers in person, I'll do 56 times 25. So when I get these, I would also do the same, 56 times 25 over 100, right? So let's put that in here. So this is 56 times 25 over 100, and I think that is a 14. So these are all 14. So that is our expected count. Easy as that, right? All right, calculate the value of the chi-square test statistic. Again, this weird looking formula. So I'm gonna do the first two. We can do it by hand, but we don't want to do that, right? So we do 3. Okay, this one. 3 minus the expected. So 3 minus 11 squared over 11 plus 12 minus 11 squared over 11 again plus this, and that. All of them. So I'm just going to do plus the last one, 10 minus 14 squared over 14. And the answer to that would be 4.61. And again, I will teach you how to do that in the calculator. But if you want to prove that the answer is 14.61, solve for all of the observed minus expected over expected. Okay, maybe it's helpful if we actually just put that in here. Let's put them all together for the sake of, not forgetting it. So 12, like not forgetting what needs to be done. Plus 15 minus 11 squared over 11. And then next plus 22 minus 14 squared over 14. 13 minus 14 squared. This is too much, right? There's no way I would do this by hand if I'm a student. Plus 10 minus 14 squared over 14. Okay? In this case, we're not being asked for the p-value, but we are going to solve for the p-value using either a table C or using our calculator. And again, what's the formula for DF? Our DF. Oh, I didn't put that on my... Let's put that one. I didn't put it on my important ideas section. So let's put the formula for DF. Where do we put that? Okay, let's put that here. DF is equal to number of rows minus 1, number of columns minus 1. There you go. So like for this example, our number of row is 1 and 2. Number of column is 1, 2, and 3, 4. So let's put our DF so that we will never ever forget. Oop, wrong. So our DF would be row minus 1 times column minus 1. So number of row, 2 minus 1. Number of column, 1, 2, 3, 4 minus 1. So that's 1 and that is a 3. So our DF here, my friends, is going to be a 3. All right, and then we will get the p-value. Either you can use the table C to get your p-value now, or you can wait until we do that all in the calculator. All right, thank you everyone, and I hope that it is not really confusing. But again, there's a difference between chi-square goodness of fit, because chi-square GOF only has one sample and one variable, but homogeneity has two samples and one variable. All right, thank you guys. I'll see you in the next video. Bye.